Hello everybody, and welcome to another lecture of 6838. It's great to see you all today, and to tell you about one of my favorite topics in the sort of geometry processing geometric data world, which is correspondence problems. Now, correspondence problems show up everywhere. Basically, the high level here is that we're going to be given two or more pieces of geometry, and our goal is to find a mapping from one piece of geometry into the other that preserves some sort of structure. So for example, maybe we want our mapping to be smooth or low distortion, maybe to preserve interesting semantic aspects of our geometry in the case of two-dimensional surfaces, and many other considerations. In fact, many of the ideas that we'll talk about today, mostly in the context of just two-dimensional surfaces embedded in 3D, also extend to very high-dimensional correspondence problems like transfer learning and machine learning. Now, today's lecture is going to focus just on that surface case, but if I have some extra time at the end of 6838, my goal is to maybe record an extra lecture segment or two to tell you a bit about transfer learning and show you that they're really not all that different in terms of how people write down these sorts of problems. So to get started, here's sort of a motivator for the problems we'll be considering today. Now here what we have are two different brain surfaces. I believe these were collected using an MRI device. And these are two different people's brains. If I recall, one of them is a graduate student, one of them is a postdoc. And so, of course, we know that there's some shared structure, but not 100%. And our goal here is to figure out which points on one of these objects, or one of these surfaces, corresponds to which points on the other. And this is one of these really interesting problems where these are two different brain surfaces. We don't expect there to be a perfect map that somehow has a ground truth here, right? Like there's no, I don't know, God-given ideal of a mapping from one brain into another that is unambiguously better than any other option. But it is clear that there are some maps that are better than others, right? Some of them are smooth and sort of carry over the high-level features from one surface to another. Others may have distortion, and they maybe are missing some interesting semantic aspects of the problem. Like, for instance, clearly there's some folds on these two brains that are somehow quite similar, and most likely the mapping that we'd want to compute should preserve those. Now, surface correspondence, especially these days, is one of these fabulous problems that's really at the intersection of many different interesting themes in geometry. On the one hand, when we solve a correspondence problem, like when we find a mapping from one surface to another, we want it to satisfy all the usual considerations that we have in geometry processing, right? We'd like our map to minimize some notion of distortion, maybe to obey certain feature points that for example, in this case, the MRI technician has chosen to be in common between those two surfaces. At the same time, there's also a data and machine learning aspect here, which I think the really modern research in the surface correspondence problem has focused on, right? Brains are a fabulous example where, of course, your brain, I say of course as if I have any idea how brain anatomy works, but my understanding is that there are certain regions on your brain surface which are very clearly correlated with different function. And that's not just a geometric consideration. I mean, who knows what's going on in the inside of your brain and the complicated structure there. But by using a bit of machine learning or hand segmentation and labeling, we somehow want that data aspect to inform the mapping that we compute. So on the one hand, we have one foot squarely in the geometry universe. We want to find a bijective, smooth mapping from one object into the other. On the other hand, we have another foot in this kind of fuzzier, data-oriented world where we suspect that there's a more complicated story going on and some structure we want to preserve beyond just curvature, geodesic distance, what have you. Now, there are many different versions of the mapping problem. And you'll notice that I'm using the term correspondence rather than the term registration, which I think is one that's a little more common in computer vision. Now, there's a continuum of algorithms from one side to the other. In fact, in past offerings of 6838, we've had some lectures on registration specifically, and maybe if I have time, I'll record them as extra segments that we're not going to view in class, but that you guys have available to each other. Now, registration problems typically are a little more conservative at least in the language that I'll use in this course, where I think of registration as maybe, I have a 3D scanner that's looking at an object and I view it from two different camera angles. And so it's the same object, just from two different views that I want to glue together, for example. Or maybe I have two different modalities of medical imaging equipment and I want to image one subject with both and kind of align them. That kind of a registration problem may involve rigid motion, or it might involve, for example, kind of non-rigidly deforming my domain a little bit. So in medical imaging, many body parts bend as the person stays in the scanner and so on. But the fundamental assumption in those registration problems is that it's kind of the same object going in twice. But today we're going to focus more on what I think at least computer graphics folks have termed correspondence, which honestly I think registration and correspondence are sort of synonyms, but in this case I think that there's a slight shade of meaning. So these correspondence problems are seeking for shared structure on pieces of geometry that I think are a little more different than would be the case in these registration examples. So for example, here we have a horse, a donkey, giraffe, and a zebra, and at least at some level of resolution, I think we can all agree that there's a mapping we could compute from one surface into another, even if we don't 100% agree on the best possible mapping at a detailed level. And that's not to say that just a smooth mapping wouldn't be valuable for applications. For example, in computer graphics applications, a smooth mapping that aligns to geometric features at least roughly is probably good enough for something like texture transfer. Whereas in some medical imaging applications, what matters more is preserving functional regions and anatomical features. So today we're going to have an exposure to many different strategies for correspondence. And what you should know is that this is a giant area of research and one that changes every year. So we're going to talk about some popular areas, mostly in graphics, and I'll give you some pointers towards some other big ideas in some other fields. And I encourage you to spend some time on Google just reading about this stuff. These are really fun problems. You might notice that I'm really enthusiastic about it, and of course the reason is that a lot of my own research is in the correspondence world. Now, in terms of applications for finding smooth mappings from domains, there are many. So one of the original motivating applications was in computer graphics in an area called texture transfer, which is exactly what it sounds like. So maybe I have an artist painstakingly draw an interesting texture, like the fur on this camel model. And now I decide that I no longer want a camel, I want a horse. Does the artist have to start over? Or maybe what I can do is compute a mapping from one domain into another and kind of push forward that texture and just reuse it. Now, particularly these days where we have these giant libraries of assets of 3D content in these virtual worlds, video games, and so on, this sort of texture transfer application I think is particularly interesting and important because we want software that can automatically come up with at least a reasonable texture for a new 3D character that we're beginning to create. Incidentally, one adjacent application, which is kind of fun and has sort of developed a life of its own in the computer graphics world, is in computational couture. So for example, maybe I 3D model a shirt to fit a particular character, like myself here, wearing all black, so you can't see the fit of my clothing, which is just as well for a math professor. But now maybe I have another character and I want to take the clothing that I so carefully tailored for one person or character and transfer it to another. In that case, there's some mapping aspect, right? I want to kind of conserve the interesting anatomical features and how those align with the clothing. And then there's another additional feature, which is sort of how the drape of the clothing, the physical fit, and so on interacts with the 3D character. We're not going to cover those algorithms in this course, but I encourage you to give it a read if you like that sort of thing. Another application of correspondence is in segmentation transfer. So a very kind of low-level task in computer vision and graphics is to take a 3D model and segment it into useful parts. So for example, once I do that, then maybe I can mix and match those parts to create an interesting 3D modeling tool, or medical imaging, maybe that's useful for finding the interesting segments in a given anatomical figure. And in both of those cases, a very standard approach would be to have an expert hand segment a few well-chosen models. And now when a new model comes in, I solve a correspondence problem that tries to find a low distortion map into one of those models where I have ground truth, and then just push forward the segments or labels onto this new domain. Another task that shows up sometimes is abstraction. This is one I've studied a little bit. So here, maybe I have a graph like on the left-hand side that I think captures some of the structure of this 3D alligator on the right-hand side. Alligator? Crocodile? I never know. But in any event, one thing I can try to do in this case is find a coarse notion of a mapping that tries to conserve structure from one into another. And then maybe I can do computations on this coarse domain, like the graph on the left, rather than this complicated mesh on the right, and still make a kind of reasonably similar inference in far less time. Now, in the computer graphics world, one really key application of correspondence is in blend shape modeling. Now, for those of you who are not familiar with blend shape modeling, it's a very simple model for deformation. It typically gets applied to faces, like what you see on the screen here. So in a blend shape, what you do is you take a bunch of different 3D models of the same character, and you put them into vertex for vertex correspondence. And there are many different ways that you might do that, right? So one way would be to take many 3D scans of the same person's face, making different poses, like what you see on the slide here. Another might be to have an artist just take a character and pose them many times, or come up with kind of different character variations or even anatomical variations of their face. And now, because they're in vertex for vertex correspondence, like I'm just using the same triangle mesh for all of these characters, I can think of each of these facial poses here as just a big vector of coordinates, one coordinate for each vertex on that triangle mesh. And I can do principal component analysis on the set of facial poses like what I have here. Now, this strategy goes back to Bland's and Vetter in the 90s, if not earlier. But what comes out is sort of some average or rest face like what I see in the upper left here, and then some PCA axes that maybe give the sort of typical whatever directions in which the geometry tends to move while staying face-like, right? Like working in the vertex for vertex basis probably doesn't make sense for facial deformation. Like just dragging one vertex of that triangle mesh is just going to create a weird singularity that I don't think you're likely to want or see in the graphics application world. So in any event, in blend shape modeling, if I want to make a blend shape model from just real world data, like scans of people's faces, one way to do it would be to take scans of faces in many different poses, put all of those scans into a correspondence tool to make sure that they're all consistently meshed with one another, and then I can do that PCA trick I described before. And this is useful in both movie studio, virtual reality pipelines, and kind of real-time graphics. And these days we see it getting adopted as one of the sort of basic linear algebraic ways of describing facial shape, even in the new deep learning world. It's kind of nice because it's a low-order set of coordinates. In fact, there are even extensions of blend shape modeling, for example, to multilinear or tensor things where maybe one axis describes who you are and another one your mood, like smiling versus frowning, and then another axis of your tensor is like what word you're trying to pronounce or what phoneme, what have you. Now, in the medical imaging world, one of the important applications of correspondence for surfaces, and also volumes, I should note, is in statistical shape analysis. This is kind of similar to blend shape modeling if you think about it. The basic idea here is that once I register or map everything to a canonical domain, like in this case in this FreeSurfer software, which was one of the typical ones people use for brain imaging, I take everybody's subjects and I map all these subjects into either one brain model that I think of as kind of average or maybe onto some canonical domain like a sphere. Now I can do things like principal component analysis, anomaly detection, basically all of the sort of statistical analysis that we know and love. It's just much easier once I've registered everything onto one domain. And so a very typical way of characterizing variability in a set of shapes is to use correspondence as sort of step zero. And this has applications in many different places. So for example, maybe I want to do a study in medical science where I take a 3D scan of many different people's organ, their liver or whatever, and now I want to describe what are the typical sort of axes where this organ tends to vary geometrically from one subject to another. Or maybe I want to measure the progress of a neurodegenerative disease. One way that I could do that potentially would be to take scans of a person's brain over time map them to one another, and then detect where the shape is deforming, or in that case, probably degrading the most. So if you read through the statistical shape analysis literature, you'll see that a lot of it is really built on these correspondence tools. One corollary of that, incidentally, is that the correspondence algorithm is really critical for getting statistical shape analysis right. So for example, if I map all of these branes to a canonical domain, but I do so poorly, so like the branes are all warped a whole lot from one to the other when I compose through the central sphere here, well, then when I do my principal component analysis, I'm going to get garbage, right? Because mostly the variation that I'm seeing is just variation in the reliability of my correspondence algorithm. It's not variation in the anatomical structure. And so there's a bit of a push-pull there, which is a little interesting. So in other words, when you look at these studies, you have to be careful to essentially make sure that what you're reading off is variability in the anatomy, not variability in whether or not your mapping tool worked. Now, similar to this application, just for fun, I also gave you all a pointer to even an application of correspondence in paleontology. In fact, there's a really well-known data set of 3D scanned teeth from, I believe it's like different species of maybe a monkey or something over time, which have evolved. And so once you map these teeth to one another, you can try to figure out like what are the interesting anatomical features that are appearing from one species to another as evolution proceeds. So here I've given you one pointer to an actual published paleontology paper that talks about a new species and some of the earliest records and uses these sorts of, in this case, conformal mapping techniques to sort of bolster their evidence for the paleontological case that they're trying to make. Notice the third author of this paper is Lippmann, who's a very well-known geometry processing researcher. Okay, so the mapping problem, broadly speaking, kind of follows the following template, which is quite vague. And we'll see that it gets posed slightly differently from one research paper to another. But the basic mapping problem here says that I'm going to take two or more shapes as input. That's my input are like two pieces of geometry, maybe expressed as triangle meshes. And my output is a mapping F from one piece of geometry into the other that maybe satisfies a few different desiderata. For one, I typically want my map to be fairly fast to compute. Now the word fast here is subjective. I actually, just last weekend, experienced an MRI for the first time, and one thing that really caught me by surprise was how slow and noisy, but mostly slow that device is. So it might be that, you know, if you just had an MRI for 40 minutes, you're happy to wait another 10 minutes for a good mapping rather than, you know, getting it instantly. Well, in some virtual reality application, that might be different. Oftentimes we want maps to be bijective or at least locally injective, especially if we're looking for a global mapping from one surface to another. Maybe we want to minimize some notion of distortion, like if I think of one surface as a sheet of rubber and I kind of stretch it onto the other, then I don't expect it to stretch all that much. And finally, maybe I want to preserve important features. So for example, in that brane mapping application, maybe somebody has painstakingly marked the important functional segments on some of these branes, and I want to make sure that my correspondence tool preserves at least those regions. Now, one thing I thought I would highlight is this low distortion bullet point because I think it aligns well with a lot of the discussion that we've had in this course and give you a bit of an idea of why even just measuring the distortion of a mapping is a bit of a tricky problem in geometry processing. These slides are courtesy of Daniele Zeus, who studied this problem quite a bit at the Technion. So here's the basic idea, which is that the application of your correspondence oftentimes basically drives what the right notion of distortion should be. And so, for example, in Danielle's work here, she oftentimes sort of distinguishes between accuracy and distortion. Like, in other words, you know, there's preserving the metric of a surface and then maybe being faithful to some ground truth, and those two considerations don't always agree. Moreover, when we talk about distortion, what we'll see is that different measures of distortion tell you that different maps are preferable to one another. So here's a nice simple example. Here we have this teddy bear model, which I believe, you know, there's one model with his arms up, another teddy bear with his arms kind of like that or something. And we've computed a correspondence from one onto another. Now, once we've done that, we can take a texture on one model and just transfer it to the other 3D model. And a very typical way to visualize your mapping is to use a texture like what we've shown on this slide, where I maybe put a grid of numbers or letters or symbols on one model, and then I'm just going to transfer that to the other, which is a great way to see how well your mapping is preserving structure and detail. Now, here's sort of some interesting terminology that Danielle introduced, and I think is a nice way to think about this mapping problem. Now, basically, what we've done is taken the texture on the left and transferred it to the same model twice, but with two different maps. In the middle image, what we see is a globally and locally accurate map. And what Danielle means by that is that locally it's preserving features and it looks kind of smooth. And globally, it's sort of aligning the big pieces of the surface. For example, you can see that the ears are mapped to one another in a nice, clear way. To contrast with that, if you look on the right-hand side, what we can see is a map that is still globally accurate, like it still takes the ears to the ears and the face to the face and so on. But locally, it's very distorted, right? The map has a lot of kind of wiggliness to it. And so what we'll see is that some notions of distortion are more sensitive to that local smoothness. Some of them are more sensitive to preserving global features and so on. So for fun, we can test our intuition for this by looking at a few different examples. So one of the things that we often do when we talk about understanding whether a mapping tool has succeeded is to generate plots like what you see on the right-hand side here. So in case you're not familiar with this kind of a plot, let me explain it a little bit. Here, the horizontal axis is error, okay? So big error is bad, but in this case, here's the sort of way that we're going to understand this. We're going to set some amount of error and say that that's tolerable. So for example, you know, this 0.05, I believe this is relative to the diameter of the whole surface. And now let's say that we have a ground truth mapping. So for example, in this human deformation case, this comes from a data set of 3D models that have already been consistently meshed with one another. Or maybe I have a ground truth mapping, which is just somebody has clicked a few points and said, like, a good mapping tool should at least preserve these 10 points. Well, one thing that I could do is say, what fraction of my ground truth is actually mapped correctly if I allow for some amount of error, right? So as I allow for more and more error, like as I move farther right on the plot that you see on the slide here, well, I would expect a larger fraction of the correspondences computed by my map to be viewed as correct. Yeah? And so when we look at the curve here, what we want is for it to kind of look like an inverted L shape or a capital gamma, right? What I want is that most of my correspondences are within a very small amount of geodesic error. Notice that this plot necessarily is an increasing function. So this is called the cumulative error graph, and it shows up in a lot of these correspondence research papers. So it's worth understanding. I'd encourage you to pause this video and kind of bond with this plot a little bit to make sure that you understand what's going on. So let's test our intuition a little bit. So here, Danielle has computed two different mappings from the left model with their leg up to these, the same model on the right twice. That's what we see. And these two different maps are both given on the slide, and we have two different plots on the right-hand side that are describing the geodesic error of these two maps. Okay, there's map number 1 and map number 2. The question is, which one is which? So which is map number 1? I'll pause for a second, let you think about it. Okay, so let's take a look at these geodesic error plots, right? So notice that essentially, what is it saying? It's saying that map number 1 basically agrees with the ground truth mapping more than map number 2. Do you see that? Because essentially, most of the matchings in map number 1 are within a relatively small amount of geodesic error, whereas map number 2 needs sort of a bigger amount of wiggle room before the mapping is correct. Now, here's where things get a little bit tricky. When we look at the surfaces on the in the images here, clearly it's the case that the figure on the right is what Danielle would call locally inaccurate, right? I mean, the map is sort of noisy at the local scale. So the question is, what about from a global perspective? And it turns out, a little bit surprisingly, actually, that the labels can be as follows. So essentially, map number 1 is actually the noisy map on the right. And this is why I think it's important to understand the positive and negative aspects of plots, like what you see on the slide here. Essentially, what's going on is that on average, that noisy map preserves the ground truth better than the smooth map in the middle, which I believe is slightly kind of rotationally shifted away. Which is to say that accuracy and smoothness, or low distortion, are not always the same thing. In fact, these two considerations can be at odds with one another. It might be that like the best mapping from a human into another is not the one that minimizes Dirichlet energy or something like that. Of course, as a point of contrast, one thing we could do might be to make a different plot. So here this is conformal distortion. Conformal distortion is basically how much does do angles get preserved in your mapping from one surface to another. And now maybe we label these two plots, map number 1, map number 2. So again, what is this plot saying? This is saying that, notice that, let's see, I can't read this slide from here. I need new glasses. Map number 2 has lower conformal distortion, right? The plot jumps up very quickly. So in other words, map number 2 preserves angles better than map number 1. And now, indeed, I think we see what's expected, which is that map number 1, which is just like all over the place, doesn't preserve angles very well on average. So the conformal distortion is quite high, whereas map number 2 is nice and smooth and actually fairly rigid looking, so the conformal distortion is low. So anyway, this is a funny example where one map preserves interesting features better than the other. Well, the roles flip-flop when what I look at is geometric distortion. So there's a whole Pareto front of different mappings that you might have. Incidentally, sometimes even the ground truth in these mapping problems can be a little suspect, right? Like, one thing that you can do, which is kind of fun, is ask the same person to label the ground truth more than once and see how consistent they are with themselves. And you can get a plot like this just for asking 2 different humans to compute a map and seeing how well they agree, and it won't be 100%. Okay. So in any event, our discussion today is just going to sample different surface mapping algorithms and model. We're going to have a graphics and vision bias today. There are a lot of surface mapping algorithms, especially in cortical surface mapping in the medical imaging world. I'm less familiar with these, but I'll give a few pointers in today's lecture. And if any of you is in medical imaging and think there's really cool literature out there that we should talk about in this course, let me know, and I'll try to incorporate it the next time we have an offering. So let's go over many different strategies for surface mapping. One of the earliest strategies, and I think the most natural, is a strategy called co-parameterization. Now, the basic idea here is that we've briefly mentioned in this course, it's not really a geometry processing course, so we didn't have many lectures on it, but when we have a surface of disk topology, right, meaning that it's kind of like a deformation of a ball in the plane, then we can take that disk topology surface and parameterize it in a bijective way onto the plane. Meaning that like, we can just compute a mapping into the plane that maybe minimizes distortion of that map. So in the co-parameterization class of algorithms, what we might do is take a surface, draw a curve network on that surface, like what we see on the top here. And basically the curve network, its role in life is to divide that surface into disk topology patches. And if we draw sort of the same curve network, or like net on the surface on the right, well, now what we can do is reduce our mapping problem to computing mappings between each of the sort of patches marked off by our curve network one at a time. And this is known as consistent or co-parameterization. Now, the machinery behind these early algorithms is basically parameterization algorithms like what we covered in lecture 2 many weeks ago. The basic idea here, if you recall from that lecture, is that we can solve a very simple, in fact, linear problem to recover a bijective map of a mesh into a plane as long as it has disk topology. This idea is called the Tutte embedding, at least when the weights are 1 or maybe 1 over distance, something like that. Or if we compute Wij, for example, as cotangent weights, then sometimes we call this harmonic embedding. But the basic idea here is that we solve an optimization problem where we have a disk that represents a 3D surface. So like here's my surface maybe. Yeah, it's kind of like maybe dips like that, like it's a bowl. It's supposed to be a bowl, in case you're wondering. See, it's sitting in 3D. Now it's a bowl. And the algorithm's goal in life is to map it to some canonical region in the plane. For example, the disk. One very simple way to do that, and remember that this is really secretly a triangle mesh, is to take the vertices along the boundary of our disk, like that, and just prescribe them to have particular position in our map into the plane, right? That's like the hard constraints that we see in our optimization problem. And then in the interior of the mesh, just treat all the edges of the mesh kind of like springs, right? That's what this energy is here. And so when we optimize for this thing, then the W's here are kind of like the spring constants. And then actually there's a really nice theorem out there. We're not going to prove it in this course. So the proof is actually a little bit annoying, called the Tutte embedding theorem, where essentially so long as the map that you've prescribed for the boundary points gets mapped to a convex polygon in the plane, the Tutte embedding, namely the minimizer of this optimization problem, which can be, again, computed just with a linear system of equations, has to be a bijective mapping. That is to say that we can't end up with two triangles overlapping in the planar domain when we do that. So what can we do? Well, now in our consistent sort of co-parameterization algorithm for mapping, we divide our surface into patches of the correct topology. We bijectively map each patch into a planar region, and then by composing through that planar region, we get a mapping from one surface into another. Now, notice that this strategy is requiring us to do a lot of stuff, right? I mean, we have to mark an entire consistent curve network on one surface and the other. Moreover, we need to prescribe what the mapping should look like along the curve network. And that's why I think this is an early algorithm, but really we don't see it used a whole lot in practice anymore. I mean, you need manual landmark. Minimizing distortion is a little bit tricky because the distortion that these algorithms are optimizing, so maybe I have a second domain here, what's really going on is that we're taking two different domains, mapping them to the same planar region, and then kind of composing through. It turns out that composing two low distortion maps into the plane is not the same problem as minimizing the distortion of a map from one domain directly into another. And so in fact, the composition of like this map and this map inverse can be quite high distortion from one surface to another, leading to like stretching of the texture and so on. That said, this is a straightforward algorithm, and it does have some guarantees. I mean, the mapping is going to be bijective in some sense, with some assumptions on what you have done to handle all these different boundaries along your curve network. Moreover, there was some effort all the way back in 2004 to alleviate the dependence on having consistent curve networks on the two surfaces. So for example, here's one, I've given you a pointer in the slides to one simple algorithm that looks for kind of a consistent set of landmarks from one surface into another, kind of look for interesting points or ones that minimize some notion of conformality, area preservation, stretch, whatever, and tries to map them to one another. I don't think that this algorithm is used much more in practice, but it is historically an interesting one. In fact, many years later, this co-parameterization idea has actually had a bit of a rebirth due to some really interesting extensions of this Tutte embedding theorem. In fact, there's sort of a series of 3 papers from Noam Eigerman and Yaron Lippman on orbifold Tutte embeddings. So remember, the Tutte embedding is this object, right? It's mapping a disk topology region in 3D into the plane in a bijective fashion. What the orbifold Tutte embedding research showed is that you can actually come up with an extension of this theorem to map objects of different topology into the plane in a bijective fashion. So for example, here's one simple one. So let's say that I have a rectangle like this. And now I'm going to add boundary conditions. So if I think of this as sort of some region in the plane, and I just ignore all of the space outside of the rectangle, then in topology, we can do some really crazy stuff. Like we can glue things to each other. So for example, let's say that I want to construct a torus, like a donut. Here's one way that I can do it. I can take this rectangular piece of paper, and I can kind of glue this edge to that edge. So if I just glue them, then I've made a cylinder, yeah? And now I'm going to take my cylinder, I'm going to glue the outsides to each other as well. Like, let's see, I always get this wrong. There we go. I think that makes a torus and not a Klein bottle. This is, by the way, sort of a standard style diagram in topology, which sort of says I'm going to start with a rectangular region. These little arrows are kind of indicating that I'm going to glue these edges together. Now, one way that I can view this is sort of like boundary conditions. So here's the kind of cool thing that these orbifold Tutte embeddings are doing, is essentially I have some surface like this torus here, and now I'm going to introduce enough cuts that the torus becomes topologically like a rectangle. So in other words, I'm going to kind of take scissors to my 3D surface, and I'm going to cut it until it has the topology where Tutte's theorem applies. Yeah, so like for example, maybe I cut the torus, around the outside, and then I make a second cut like that, right? So that kind of corresponds to undoing this procedure that I've drawn you here. Well, here's the kind of cool thing that the orbifold Tutte embedding does, is it adds boundary conditions to the basic Tutte algorithm. So for example, it says that like points on the two sides of the cut maybe actually end up quite close to each other modulo these identified sides. These can be formally made, these can be made formal by kind of doing some certain linear conditions on the mapping. And what they show is an extension of Tutte's theorem to these boundary conditions, which essentially allows you to directly map domains that don't just have distopology, but maybe have topology of, in this case, a torus, or in this case here, I guess, a sphere, directly into the plane by essentially just introducing clever boundary conditions. And now what we get is a consistent co-parameterization style algorithm for mapping one surface into another that doesn't require that whole curved network along the surface. Now, what this doesn't solve is the problem of minimizing distortion, right? You're still minimizing the distortion of two maps into the plane instead of a map from one surface into another, but it does sort of alleviate the dependence on these consistent curve networks and gives a really nice way of understanding this mapping problem. And in fact, Tutte's algorithm really does lead to basically a conformal map, like an angle-preserving one. So the distortion of these things really isn't so bad in practice. So you can read, for example, the diagram on the bottom here by identifying the colored vertices and edges. So there have been actually a whole series of orbifold Tutte embedding papers that map into a planar domain, and then a spherical domain, and a hyperbolic domain. And these are cool for surfaces of different topology. It turns out you can, depending on the topological structure, there's some canonical domain you might want to map into. We don't have time to cover this in detail in this course, but you really should give these papers a read. They're super interesting and a really clever idea. One last note is that the distortion of these maps tends to be concentrated right at these cone points, like the corners of this mapping. So when you're looking at their figures, be sure to look really closely at those. Finally, I should note that this co-parameterization approach actually has a really long history and goes back outside of the computer graphics world to neuroimaging. And in fact, in the neuroimaging world, what's popular is to co-parameterize not on a planar domain like what I've drawn for you here, but actually on a domain like the sphere, which does make some sense given that, well, for example, brain surfaces topologically are really spherical objects. So one of the really popular tools for neuroimaging and geometric analysis in that world is some software called FreeSurfer. I actually don't know where the name comes from. A lot of this medical software has kind of funny names. There's FreeSurfer, Spherical Demons, and so on. And FreeSurfer, actually, just last night when I was preparing for today's lecture, I gave their paper another read, this cortical surface-based analysis paper. It's back from the 90s. And it actually anticipates a lot of the challenges that we talked about in graphics and geometry processing many years before they occurred in that community. It's really worth a read. It's some interesting stuff. Moreover, their algorithm is sort of a clever technique. They call it inflation for taking a 3D brain, and in their case, they can formally map it to a spherical surface. So if you have a whole collection of brains, they all get conformally mapped to the same sphere. And they're basically making use of some ideas in sort of conformal shape analysis, which says that you can conformally map things to spherical domains without any distortion in the angle. So this course doesn't cover a whole lot of conformal mapping. I think Keenan Crane's course at Carnegie Mellon probably does a lot more of that. But it's worth a read, and really was the beginning of a lot of the conformal geometry that we know and love in the graphics world as well. Let me pause for a second and clear out the screen here. Okay. Now, of course, related to the co-parameterization problem, I thought I'd spend just a few minutes with a quick digression to a related problem, which is just parametrization. And typically, this term refers specifically to mapping a 3D surface into the plane. Now, if this were just a purely computer graphics geometry processing course, we'd spend a lot of time on parametrization. But I think this is one of these techniques where you all can probably read the literature on it quite easily, given the discussion we've had in this course. So I'm going to largely leave you to do it on your own, but I did think I would spend just a few minutes telling you a bit some of the interesting ideas in this space. Now here, this visualization is sort of similar to the one with all the numbers mapped on a surface that we saw before, but now we're just taking a checkerboard on the plane and mapping it into a 3D surface. And what we're showing are the steps of one of the popular surface parameterization algorithms out there known as scalable, locally injective mapping from Rabinovich and colleagues in 2017. In the context of 6838, I think one of the fun ways to understand many of the modern parameterization algorithms is that they're just large-scale optimization techniques. The basic idea of almost all of the sort of recent SIGGRAPH papers in this space is illustrated here, where we have a mapping of our 3D surface into the plane, and in the parameterization problem, really our variables are just a two-dimensional coordinate per vertex on the mesh, right? Which is telling you for each triangle on my 3D surface, maybe it's already cut into this topology, where should its vertices go in the plane? So all of these algorithms have a very similar flavor. They're optimizing some distortion measure like what you see on the slide here, where it's just the sum over all the triangles of the area of the triangle times some notion of the distortion of that triangle when it's mapped from 3D into the plane. Notice that distortion is actually necessary because the plane has zero Gaussian curvature. The surfaces typically do not. So when I map it into the plane, something has to bend or stretch. But there are many different notions of distortion, and each one will lead to a different level of difficulty for the optimization technique. Now, typically, the way that we can measure distortion is as follows. Essentially, if we know where the three vertices of our triangle go in our parameterization map, remember from our lectures on the Laplace operator that we can take that map and kind of interpolate it to the interior of the triangle using piecewise linear finite elements. So in other words, basically, what we're going to assume is that when we restrict our parameterization map to the interior of a triangle, we're going to think of our map as just being kind of locally linear affine. So if we do that, then essentially the map looks like what I've shown you above the yellow arrow on the slide here. It's basically just a Jacobian matrix J multiplied times the coordinate plus some constant C. That's it. And so most of the distortion measures basically are just functions of that Jacobian matrix. For example, maybe they want the singular values of that matrix to be close to 1, which would mean that your map is kind of rigid. Or maybe it wants that the ratio of the singular values is close to 1, which would make your map look conformal, right? Like kind of angle preserving, because in that case, it doesn't care about uniform scaling. So more generally, you can understand a lot of parameterization techniques by proposing different distortion measures for individual triangles, summing over the whole mesh, and then having some strategy for reducing distortion, which might be as simple as gradient descent or Newton's method, or might be, more complicated than that, like, ADMM, some non-convex optimization, and so on. One of the amazing things is just the huge numbers of different distortion measures that are out there that can measure the quality of your surface parameterization in different ways. So here's a nice table from that scalable locally injective mappings paper I mentioned before. And this is just a selection of the many distortion measures that have appeared in the literature that are reduced from by different algorithms, right? So some of the simple ones, like the least squares looking ones, maybe are even optimizable using a linear solve. Others, like the symmetric Dirichlet energy, which involves like the inverse of the Jacobian matrix, becomes much more complicated to optimize in practice, and maybe even becomes singular when a triangle is nearly going to collapse to make sure that your mapping is bijective at the end of the day. So I encourage you to give this paper and the ones that cited a nice read. I think they're very straightforward to understand, and they provide a lot of really nice insight into this parameterization universe, which is a really fun large-scale optimization problem, which basically contrasts in every way possible from the large-scale optimization that we see is popular in machine learning, right? Like these are tons and tons of little local terms that all have to be resolved to create a mapping, which is quite different from like parameterization, or rather like stochastic gradient descent, where you've got a lot of data points and it's okay to throw some of them out in any given step. So in any event, these are really fun problems to think about, and I encourage you to give them a close read. Incidentally, there is very recent work that I thought I would highlight for you guys and just to send you to go take a look at, which actually tries to combine some of these strategies. So here in this distortion minimizing injective maps between surfaces, all these papers have very similar titles. The basic idea here is that maybe we use these Tutte style strategies to co-parameterize two surfaces, which is useful for getting an initial mapping which is bijective from one surface into another, but it's not necessarily very low distortion. So then after that, you can do essentially adjustment of those co-parameterized maps to reduce the distortion of the composed map. Now, this is an idea that's been kind of around verbally for a long time, but I think was very hard for people to implement correctly because you're sort of optimizing the distortion of this composed object by dealing with this common domain that's in the middle. And there are a lot of kind of headaches that appear. Like, for instance, you're kind of dealing with the overlay of two triangulations in the plane. This paper, there's a lot of engineering and a lot of math that happens to get it to work. And I think it's a really promising, interesting direction that we'll see some more work on in the future, but only for people that are pretty brave when it comes to implementation. I actually considered some problems like this years ago and put them aside because it was just too much. So it was really cool to see these guys make this work out in practice. So in any event, that's our end of our digression into surface parameterization. Let's get back to surface correspondence. And here's another idea. So the correspondence algorithms we talked about so far are mostly dealing with sort of short distance interactions, right? Like these parameterization algorithms just want every triangle, which are like little tiny facets along our surface, to be distorted one by one, not very much. But a different thing I could do would be to compute some long distance along the surface. For example, the distance from my left hand to my right hand. So the length of this entire path, and then ask that when I map from one surface into another, that long distance should be preserved as well. Now, one thing to note is that these are not the same thing. I mean, obviously, a map that preserves short distances perfectly also preserves long distances. But it could be that I chain together lots of little local distortions, and then globally, my surface map like drifts quite a bit. And so these long distance interactions can really stabilize the computation of a map, and actually make some of these algorithms a little more efficient and predictable. So sort of the opposite scale from these algorithms which are optimizing the Jacobian of a map are algorithms that optimize a very different notion of distortion, known as the Gromov-Hausdorff Distance. This has come up a few times in this course, I believe. But here's really where it shines. So the Gromov-Hausdorff distance is actually just a distance between two metric spaces, x and y. All I need is a distance metric in order for Gromov-Hausdorff distance to be a distance. And the Gromov-Hausdorff distance can be written as a minimax problem, like what I give you on this slide. Now this is, I think, a little hard to parse, so let me see if I can do an okay job of doing it. So let's say that I have a map from my domain x on the left-hand side into my domain y on the right-hand side. And I'm going to call my map phi. And I want to know whether my map preserves not just local geometry, but actually global geometry as well. That's what the Gromov-Hausdorff distance is after. Whether it really is a distance between metric spaces in the triangle inequality sense. Now here's where things get a little bit tricky. There's sort of a second order relationship that I have to resolve. Let me see if I can phrase my sentence properly. Here's the way it goes. I have a low distortion map if I can take x to y and x prime to y prime. If those pairs of points are mapped to one another, then the distance from x to x prime looks like the distance from y to y prime. Okay, so I think that's actually better expressed in this diagram, in this equation here. The basic point here is that if two points get mapped to one another, then they're distance in the pre-image should look like the distance in the post-image. So the Gromov-Hausdorff distance says that the distance between metric spaces does the following thing. It says, I'm going to look for a map from X into Y that optimizes a supremum, where the supremum is the pair of points with the worst possible distortion. Okay, so the basic idea here is that the map phi here is trying to find the map that preserves pairwise distances the most, where the amount of money that I pay for a given map is just the worst distortion of one pair of points. You see that? So like what's going on inside of the absolute value here is the difference between the distance between x and x prime and the distance between y and y prime. And I look over all possible x prime pairs to find the worst possible one. That's how I judge a map phi. And then the optimization problem for maps is to minimize over all possible maps, that distortion measure. I know that that sentence is a mouthful. I encourage you to pause this video and kind of think through it a bit. And I think you'll convince yourself that this is a pretty reasonable model for computing a map, but it is quite coarse, right? What it says is that if I have one bad mapped pair of points, then the rest of my map can be total garbage so long as the level of garbage is less than the distortion between that single pair of points that realizes a supremum, which is a bit pessimistic. What it means is we don't care about average case, just worst case. And we're going to see that there's a variation of this that looks at the expectation instead. Now, if we go all the way back to our distance metric embedding algorithm, one of the algorithms that we talked about was a technique called classical multidimensional scaling, which we motivated as basically computing eigenvectors of a distance matrix as a way to embed distances into a Euclidean domain. To compute a mapping from one surface into another, one of the early popular techniques for doing so was proposed by Bronstein, and Kimmel in 2006, and it was known as GMDS, or Generalized MDS, which essentially was looking for a permutation of the points of one surface onto another that optimized that Gromov-Hausdorff distance. And so, so this was the GMDS model. The only problem is that the space of permutations is really big, right? Moreover, you're assuming that the two surfaces are discretized with the same number of points, but even if you're willing to make that assumption, like maybe you just subsample, that optimization problem for Gromov-Hausdorff is quite difficult. In fact, it is an instance of a problem called the quadratic assignment problem, or QAP, which is NP hard. This is different than the linear assignment problem, which is like that optimal transport problem we talked about in a previous lecture. Now, many quadratic assignment problems appear in the surface correspondence universe, and the basic reason is, basically quadratic assignment from an optimization perspective is like optimizing over the set of permutation matrices, just some quadratic objective. And the reason that these quadratic objectives are so common in correspondence is that they kind of are capturing some second order relationship, right? They're saying like, if x goes to y and x prime goes to y prime, then the distance from x to y should look like the distance from x prime to y prime, or whatever. I think I got that wrong. Like go back to that Gromov-Hausdorff slide and rephrase as needed. But those sort of second order relationships are what make quadratic assignment so difficult. In fact, difficult enough that it's equivalent to many other NP hard problems, which we don't know how to solve in the most general case. But it turns out that specifically for surface matching, oftentimes this general quadratic assignment problem is a lot easier than the most this quadratic assignment problem is a lot easier than the most general notion, with the crazy counterexamples you see in complexity theory. But things can go wrong. I mean, the basic issue here is that there are very often many local optima in these assignment problem style algorithms for surface mapping. And the reason for it is staring you right in the face here. I mean, for instance, if I write an algorithm that's trying to preserve geodesic distance from one surface to another, you can see that the problem is non-convex in the sense that there are two equally good maps, right? There's the one that takes left hand to left hand and right hand to right hand, and then there's the one that inverts the entire surface. And both of those maps actually have equally good distortion of the geodesic distance metric along the surface. So right away we see that there's at least two local optima of our mapping problems that are kind of well separated, which is what makes QAP so difficult relative to its convex friends in the linear assignment world. So in any event, over the years, there have been many different strategies for optimizing this generalized multidimensional scaling algorithm. We'll mention a few. The basic trade-offs here is that, it's a good distance for non-isometric metric spaces. It really doesn't make any assumption on geometric structure, but you have this ginormous non-convex optimization problem that you have to solve. In practice, there are many different algorithms that attempt to do so anyway. I've highlighted a few in the course slides. So one simple thing that you could do would be to discretize your surfaces really, really coarsely so that you're actually in a regime where you really can solve the GMDS problem. So maybe I sample my surfaces with like 10 points and I can solve a problem with like size 10 factorial, or maybe even a little larger if I do some clever pruning. And then once I have the solution to this extremely coarse GMDS problem, I then just kind of interpolate the matches, maybe based on distances to the closest landmark or something like that. I can come up with a coarse-to-fine sort of heuristic algorithm that maybe does something like the previous slide, like solves a very coarse algorithm, then iterates with a finer approximation of the surface, but tries to throw out bad matches in a conservative fashion so that the search space isn't so large. So for example, this 2011 paper attempts to do that in a kind of controllable fashion, and I believe does pretty well. And one of the other kind of things to note in practice, it's kind of a weird third bullet point, I guess, it's just that GMDS also has been extended in clever ways to cope with partial matching, which is even harder. So now you can't rely on the marginals of that permutation matrix. So for example, if I want to map a human to a centaur, then I need to identify not just a good low distortion map, but also which parts are actually present in the two surfaces. There's some clever ideas for how to extend in that direction, e.g. by kind of alternating back and forth between one of these GMDS techniques and something that's sort of sub-selecting pieces of a surface. So if we return to our list of desiderata, I would say GMDS is unlikely to be bijective or fast to compute, but it is low distortion in a global sense, and often can preserve important features, especially thanks to this sort of idea of dealing with long distances explicitly. Now, more recently, there's been a variation of this GMDS problem, which I believe has better empirical performance. It still has similar theoretical hangups, but I think the optimization landscape for this problem tends to be a bit easier and has actually shown some practical performance in real-world application, which is instead of doing the Gromov-Hausdorff distance, we compute a different thing, which is the Gromov-Wasserstein distance. Now, you might remember that name Wasserstein from our lecture on optimal transport. Remember that optimal transport lecture was all about the sort of expected work it takes to displace one probability measure onto another. In the Gromov-Wasserstein distance, we compute the expected distortion of a distance metric under a mapping. So now our mapping is captured using a measure coupling gamma. That's just like our lecture on optimal transport. Remember, gamma is like a probability distribution on the product of two domains. That's big when we think that things should be matched to one another. And now we have this double integral, which is basically exactly the same as that minimax problem in Gromov-Hausdorff, but rather than measuring the highest distortion of a fixed map phi, we're instead looking at the expected distortion of this measure coupling gamma, right? So gamma is big whenever I think that x and y should be matched together. So if you kind of read through this formula, it's saying a very similar thing, right? Like if x goes to y and x prime gets mapped to y prime, right? That's sort of the and is being implemented in that product here. Then the amount of money that I pay is the distortion of the distance metric, like the integrand. Now, this is also a quadratic assignment problem. Notice that there's two d gammas multiplied against each other, but in practice, this seems to have a smoother objective landscape that's a little bit easier to optimize. So this work goes back to Memoli in 2007, but in the years later, we've come up with different practical algorithms for actually minimizing this objective in practice. Again, only reaching a local optimum. If we could find a global optimum, then P would equal NP, and we'd be making a lot of money. So for example, remember that we covered this strategy of entropic regularization in optimal transport lecture. We can actually entropically regularize the objective function in the Gromov-Wasserstein distance, and then what you end up with is this algorithm that actually I called the entropic metric alignment algorithm, which is basically a small extension of that Sinkhorn technique for entropy regularized optimal transport, and you can prove that it converges to a local optimum of this, this non-convex problem, which is pretty nice. A different way that you can go, if you really care about the global optimum of these sorts of quadratic problems, is to use a semi-definite programming relaxation. So Yaron Lippmann, whose name has come up a few times in this lecture, has considered all kinds of clever relaxations of this problem, which often have this property that they call tightness, meaning that I relax the constraints of my QAP, I optimize, and then I kind of observe that I got the permutation matrix that I wanted anyway, meaning that I recovered a global optimum of this problem. This SGP paper that I've pointed you to was some of the early work on convex relaxation of matching problems. And there's sort of pros and cons. I mean, the pros are that you get the best possible mapping. The cons is that this is a SDP, a semi-definite program that scales something like quartically in the size of your mapping problem. So you can see that they're solving it on like 8 points per octopus here. Some of their follow-up work really reduced the computational load and made these SDP relaxations a little more practical. I think they're still maybe not competitive with some of the fast non-convex algorithms that have fewer guarantees, but this sort of lives in some landscape. Okay, so I think we've covered two ends of a really big continuum, or at least we've so far, I guess, covered really just the left end of a big continuum, which is to make very few assumptions on the input data for your mapping problem, right? So for instance, in multidimensional scaling, or generalized multidimensional scaling in Gromov-Hausdorff, we're just trying to find a mapping from one metric space to another that minimizes some notion of distortion. And as we saw in our metric space lectures, the assumption that a space is a metric space is a really, really weak one. On the other hand, we could make really strong assumptions on our input data and then come up with very different geometric algorithms. So for example, we actually already covered a mapping algorithm a few lectures ago when we discussed the Laplacian operator, and that was to use this heat kernel map object. And so this would be an example of an algorithm that makes very strong assumptions on the input data and then can compute a mapping. So in the heat kernel mapping algorithm, what we did is we assumed that we're given two surfaces that are actually isometric to one another. Moreover, they don't have too many symmetries. And we're only going to make an algorithm for mapping that works for isometric surfaces. So if our surfaces are non-isometric, we don't have any guarantee at all. When they're nearly isometric, well, we also don't have a guarantee, but these algorithms get applied in that case anyway. So for example, an elephant versus an elephant with its feet slightly up is probably a good example of a very close to isometric map. And what the heat kernel mapping paper showed back in 2010 was that essentially if somebody maps just 1 point on those two isometric surfaces, then I can recover a bijective isometry from one surface to the other just by computing this per vertex descriptor and just doing closest point matching. This is one of these ideas that works great in theory, but in practice is a lot harder. So the pros here are that it's a tiny, tiny search space. There are some extensions to partial matching that are out there. But if your input data is no longer isometric, then you can get some really poor mapping. So for instance, on the bottom right here, there's a figure from, I believe, the blended intrinsic maps paper we'll cover in a few minutes. And you'll notice that the mappings computed using this technique, when they use it to just transfer color from one model to the other, have many serious deviation from being even continuous in this case. So now we have really a continuum, right? We have Gromov-Hausdorff algorithms, which make basically no assumptions on your input data and try to get a pretty good map anyway, but they're very expensive computationally. On the far right-hand side, we have algorithms that assume your input surfaces are isometric and then can compute maps, but when your input data is not isometric, don't work too well. A reasonable question is what's in between, and there's a whole lot of work out there that tries to explore that space. One of the popular approaches is to work in the space of conformal mappings. Now, we've talked about isometric mappings a lot in this course. Those are ones that preserve angles and areas. Isometric mappings are ones that just preserve angles, so they allow there to be all kinds of area distortion so long as angles get preserved by the Jacobian of your map. And it turns out that computing conformal maps between surfaces or from a surface into a canonical domain like the plane or a sphere is a much easier problem and a really, really well-studied one in graphics. In fact, this work dates back to 2009, which is quite a long time ago in graphics language. But even since then, there have been a ton of work on conformal parameterization and even more sort of detailed mapping techniques for conformal surface geometry. So here's the kind of cool thing. Unlike composing low distortion maps, where I might have two low distortion maps through a sort of intermediate domain that compose to a high distortion map, it turns out that if I compose two isometric maps, I get another isometric map. Or, oh my gosh, I got that wrong. I'm sorry. If I compose two conformal maps, I get another conformal map. And remember that conformal maps are sort of a superset of the set of isometric maps, right? Remember that isometric maps preserve angles and areas, conformal maps just preserve angles. So essentially what these Mobius algorithms are doing, these Mobius voting techniques and so on, is essentially using the fact that it's quite easy to search in the space of conformal maps to find the nearest to isometric map within that space. I think I managed to tuck myself into a corner, so let's try that one again. Here's a basic intuition for these algorithms. What we're going to do is we're going to take our input surfaces and we're going to map them conformally into a domain where it's kind of easier to do our computation. So in this case, the extended plane, which is R2 plus some points at infinity. And it turns out that you can conformally map them using something that's close to a linear system of equations. Now, a fact that we're not going to prove, because this is a survey lecture to be sure, is that a conformal mapping is actually defined just using 3 points. We're going to see how in just a minute. So here's what basically goes on. We take the two pieces of input geometry, like these two cats, and we map them both into the plane in a conformal fashion. So now we have an angle preserving map from one cat into another by going into the plane and then back out. And now what we're going to do is, rather than searching in the space of maps directly from A into B, from one cat into another, we're going to just look at the set of maps that are conformal maps of the plane, so that we're sort of using the following diagram, where we've mapped the two surfaces into the plane, and now in between there's a map of the plane to itself that also preserves angles, and we compose all these things together, we get a conformal map from one surface into another. The basic idea here is that the biggest amount of headache is conformal mapping of a piece of surface geometry, but we only have to do that once for the two input surfaces, and then we can search over a big space of maps just by mapping the plane to itself many times. This is kind of a clever idea, and moreover, you can find a perfect isometry between these two surfaces if one exists in n-cubed time by just taking all possible triplets of points on these surfaces, mapping them to one another in this planar self-map, and finding the one with the lowest area distortion. Now, what makes these algorithms so efficient is the idea that the conformal maps of the plane, this downstairs domain, are actually parametrized in a really nice way, and these are known as the Mobius transformations. Now, there's a little short video that I can play that basically defines what these are. I think I've set up our video system to play it properly. Unfortunately, I cannot hear it as it plays, so hopefully we'll be able to hear the audio as he talks.
Mappings in geometry, with applications from brane mapping to relativity theory. A Mobius transformation sends each point on the plane to a corresponding point. They're built from 4 basic types. The simple translations, dilations, rotations, and inversions, which turn the plane inside out. Lines on the plane either remain lines or transform to circles, and right angles stay true. In general, a Mobius transformation can be a complicated combination of all four effects. The true unity of Mobius transformations is revealed by moving into the next dimension. Taking a cue from Bernard Riemann, we place a sphere above the plane. A light at the top shines through the spherical surface.
All right. So the video also describes a stereographic projection, which is a nice
As the sphere moves,
interpretation.
the points
But
on the
I'm going
plane
to pause
follow.
it, even though I can't quite hear what he's saying.
When the sphere translates,
only another minute.
so does the plane. Raising the sphere gives dilation. Spin the sphere like a top, and the plane rotates. Rotation about a horizontal axis corresponds to inversion. Even the most complicated Mobius transformations are revealed to be simple motions of the sphere.
Okay. So the other ingredient that goes into this Mobius voting technique is an algorithm called mid-edge uniformization. Uniformization is generally a term for the sort of conformal mapping strategy. I'm going to skip over that and let you guys give it a read because I think this technique has probably been replaced several times over since this original paper. But essentially it gives you a way to map a spherical surface into the plane conformally with a reasonable discretization of the conformal structure. So at the end of the day, the Mobius voting algorithm looks like what you see here. Well, what we're going to do is we'll take our two input surfaces and map them into the complex plane in a conformal way. And now, for every set of 3 points on one surface matched to 3 points on another, I'm going to find a Mobius transformation of that underlying plane that takes those 3 points and identifies them in their images. And now I'll look at the area distortion of that conformal map I get by composing surface to plane through Mobius back to surface. And I'm going to just kind of tally a vote for pairings that tend to lead to a low distortion metric and do this many, many times for different triplets. What you end up with is this voting technique, which just randomly draws lots of triplets of points, maps them to one another, evaluates the distortion, and then keeps track of pairs of points that tend to lead to low distortion maps. And then if you just look at that sort of tally matrix, what you get after rounding off is a pretty nice mapping. So this is an efficient technique. The voting procedure can deal with some amount of non-isometry, not a ton, but some. But on the other hand, there's no guarantee that what you'll get out is smooth or continuous. And it doesn't really optimize any notion of global distortion, just kind of local stuff. One detail of this algorithm that probably could be addressed using some more modern techniques is that it only applies, at least directly as it's been described, to genus zero surfaces like spheres, because those are the ones that can be conformally mapped into the extended complex plane using this uniformization technique. Now, an extremely well-known algorithm which has really survived the test of time and remains the sort of basic baseline in the mapping literature is a technique that was called blended intrinsic maps and is built a lot on that Mobius voting idea. So in blended intrinsic maps, you're also going to compute a bunch of conformal maps between two surfaces. But now, rather than just voting for pairwise correspondences, the idea is to subselect just a few conformal maps and then kind of average them together into one map that is maybe no longer conformal, but now has much better area distortion and is still kind of continuous looking. So what you end up with are diagrams like what you see on the left-hand side where the surface is colored, saying that like maybe the left arm prefers this one conformal map, the right arm prefers another conformal map out of the possible sets, and then there's some blending weights in between them that kind of smoothly transition from one mapping into another. And this algorithm is one that still appears as a sort of baseline for tests in mapping algorithms today. So the basic algorithm here is, once again, similar to Mobius voting technique. We're going to generate tons and tons of mappings by maybe doing this mid-edge uniformization and then randomly pairing triplets of points to compute conformal maps. And now, once we have this huge set of maps, we're going to try and find some set of them that is consistent. So for example, maybe your conformal maps actually cluster into two categories, those that take your left hand to your left hand and those that take the left hand to the right hand. So I just want to find a consistent subset that deals with one of those, but not the other. So how do they do that? Well, it's actually an application of some of the machinery that we've already talked about in this course. It's basically just a spectral clustering algorithm out there that takes a collection of maps, does some spectral clustering on it, and comes up with a subset that somehow agrees with one another. So for every pair of conformal mappings in their collection, they compute some number that describes how well they agree, and then they find a subset that agrees particularly well. And so that's just done with eigenanalysis, just like maybe the normalized cuts algorithm that we talked about in class. Now, after you do that, we're going to compute blending weights for each point on these mappings. Remember that blending weights are essentially telling us the influence of each of these conformal maps on our final output. That can be done, for example, just using the area distortion of the different constituent maps at a given point. And then there's just a simple averaging procedure to glue them all together. So this is definitely a piece of engineering. I think that there are very few guarantees on this BIM algorithm, but it does tend to work well in practice, and it really is one that's seen a lot of adoption. You can see some really nice mappings here that are used to transfer color from one surface to another, which is another visualization, which is a bit more forgiving the visualizations we saw from Daniele Zuz earlier in today's lecture. This was also one of the earliest papers to introduce those plots, like what we talked about in class. You can see that this paper, by the way, the color here is trying to illustrate a bit about the different geodesic errors, at least the sort of amount of wiggle room there is. You'll see that these maps are not terribly accurate. I mean, there's a lot of follow-up work that really improved this idea, but the basic idea of blending maps was sort of the first one that really aimed to make bijective smooth mappings from one surface to another, and it really was quite successful. So it could handle 9 isometric shapes, it's fairly efficient, but there could be a lot of area distortion, and this algorithm still only dealt with manifold G and 0 surfaces because it relied on that conformal mapping machinery. Now, for one last topic that we'll cover in today's lecture, I thought I would step back and highlight one subtlety in the correspondence world that we really haven't mentioned in today's lecture yet, but is really critical. And that's the question of how do you represent a map? Now, this is a kind of funny thing to think about. I mean, in some sense, a map in the mathematical sense is quite easy to capture, right? It's a thing that takes points on one surface, outputs points on another. But there are actually many different ways to discretize mappings, right? I could think of it as a permutation matrix, but then I'm kind of requiring my two meshes to have the same number of vertices. Maybe it's an approximation of some smooth function, like that just maps a mesh into the 3D space close to the other mesh. Maybe there's a probabilistic relaxation. I go to the Bayesian world. All of these different representation considerations are really tricky. So for instance, what does it mean for a map to be invertible if my map is from one triangle mesh into another? It's not such an obvious question to answer, and I think there's actually not really consensus in the literature for what invertibility necessarily means. There are many different definitions out there, and all of them have some drawbacks. So in a very different thread of literature in the correspondence world, essentially people considered many different representations for maps. For example, in some of my own research, I studied a lot of problems that involve thinking of a map like something that takes points on one model to probability distributions over another model, which is a nice way to relax these problems into smooth ones. A different relaxation, which is particularly popular in the graphics world, was something called functional maps, which I've illustrated here. So here I've got two different surfaces, M0 and M. And let's say that I do have a mapping from M0 into M, right? So here I've got a phi, which takes every point on M0 and outputs a point on M. Maybe it's smooth, low distortion, whatever. So a term that you see a lot in the functional mapping literature is that this is a point-to-point map. It takes points on one domain, outputs points on another. Now, let's say that I do something kind of funny. I take a can of spray paint, like these rainbow colors you see on the slide here, and I spray paint the surface M on the right-hand side. Okay? So I have a map phi from M0 to M, and I put color on the right-hand side, on M. I claim that I can take that color and use phi to put colors on the surface M0. How do I do that? Well, for every point on M0, I follow phi to its corresponding point on M. I look at the color that I see, and I copy it back to the original surface. Now, of course, color here doesn't matter. What really matters is that for any scalar function that maps from M to the real numbers, like for example, from M to RGB color, now I have, given a map from M0 to M, I have a way to map M0 into the real numbers in a consistent way by composition, right? So in particular, if I have a map from M0 to M, then I have a way of taking functions on M and pulling them back to functions on M0, right, by composing, right? That's exactly the second equation in the box here, right? So for every function f of x on the right-hand side, I have a new function, which is the pullback, where essentially what I'm going to do is follow phi to the other surface, and then evaluate f of x. So what does that mean? For every forward map from left to right, I have a functional map from right to left that takes functions on the surface on the right and outputs functions on the surface on the left just by composition, right? These two things are sort of in bijection of one another. So this is kind of an interesting covariant contravariant structure, right? For every map from A to B, I have a functional map from B to A, which takes functions to functions. Now, for those of you who are mathematicians, you might kind of feel like that has something to do with category theory. I think that is indeed the case. One of these would be like covariant and the other is contravariant. I personally find category theory to be a terrifying area of mathematics, so I'm not even going to bother to try and make that connection. But if you can do that, that would be great. So the idea of functional maps here is that rather than trying to take points from M0 to M and optimizing over the set of maps, instead, I'm going to optimize over the set of operators that take functions on surface M and pull them back to functions on surface M naught. And this turns out to be a really powerful idea that's connected to many of our previous lectures. In particular, our lectures on the Laplace operator. So remember that I can take any function on a surface, that's an L2, and I can write it as a linear combination of the Laplacian eigenvectors, which are these psi i's. So for example, here we have the eigenhomers, and I can take any function and write it in the span of these things. And a very reasonable approximation is to just work in the low order eigenbases, like, just the first couple eigenfunctions. So in any event, I can think of a functional map like a matrix, right? That is to say that for every surface, for every function on one surface, I can write that function in the Laplace-Beltrami basis, right? So that would be like computing these coefficients AI. And now when I multiply that vector of coefficients AI by my functional map matrix, what it gives me back are the coefficients of the corresponding function mapped to the other surface, and the other surface's Laplace-Beltrami basis. And so in other words, what functional maps gives you is a really interesting representation of a map. It doesn't take points to points, it takes a basis to another basis. It's just a matrix. And so for instance, here we have two different cat models. And essentially what we've done is by just composing functions with these maps, I can take every function on the first domain, map it to the other domain. In this case, these cats are in correspondence, and then write the same function in the Laplace-Beltrami basis of the other surface. That leaves me with a matrix like what you see here. And there was a really interesting empirical observation that we made, which is that this matrix actually looks very close to the identity matrix when I write my functions in this Laplace-Beltrami basis. And that kind of makes sense, right? Like a low frequency function on one surface tends to get mapped to a low frequency function on another surface. And in fact, you really can formalize that notion. So for example, if a mapping is isometric, then it turns out that the functional map in the Laplace-Beltrami basis will be a diagonal matrix. In fact, if I have a high distortion map, like I try to map the head of one cat to the tail of another, I end up with a matrix which is extremely dense. It's not sparse at all. And so this high-level observation that I could describe maps using matrices led to a huge literature on algorithms for computing functional maps in practice, and it's been studied to death in the graphics universe. There are all kinds of really clever functional maps out there. So here's the basic idea of what goes on in these techniques. I compute a bunch of geometric features on one surface and a bunch of geometric features on the other surface. So for example, maybe I compute the heat kernel signature on these two domains, which are just a bunch of functions on one surface and the other. Okay? Here's the thing. If I have a good map, then my map should take all of those descriptor functions, all those geometric features, and map them to one another. In other words, if I think of a matrix B as containing, the per vertex values of some function on my target surface that I think should be conserved under my map, then I should have this relationship that B equals C times A. So for example, let's say that I assume that my map is isometric. Well, one thing we know about isometric mappings, thanks to Gauss's Theorema egregium, is that the Gaussian curvature should be preserved under any isometric map between surfaces. Now, Gaussian curvature is a thing that I can compute in a vacuum from just one surface, right? Remember, we talked about many algorithms for computing Gaussian curvature. So what could I do? I could say, okay, I'm going to compute the Gaussian curvature on one surface, the Gaussian curvature on another surface, and now, when I'm computing my functional map, this matrix C, what do I know? I know that C times the Gaussian curvature function on one surface should give me the Gaussian curvature function on the other. And this is a linear constraint on our functional map. So if I compute enough descriptors, I can actually just recover my functional map based on a linear algebraic solve, right? One that just puts, in least squares sense, all of these different geometric features in correspondence with one another, right? So what does that mean exactly? Let's see if I could write this out a little more detail. So let's say, again, that I have two isometric surfaces. And this is not an assumption for all functional mapping algorithms. This is just a simple example. So let's say as input, I get isometric surfaces like that. Okay? So now here are my two surfaces. Notice they're basically the same because they're isometric. And now, what can I do? Well, I could apply, for example, the algorithms that we've already talked about to map these two surfaces to the real lines by computing the Gaussian curvature. So if I call, I don't know, this is surface A and this is surface B, then I have Gaussian curvature function A and Gaussian curvature function B, right? And maybe the curvature function is high, like here, because there's, the surface is kind of bendy, whatever. So now, if I have a functional map, right? Let's call C our functional map. Then what do I know? Well, I know that if my map is truly isometric, then C times the Gaussian curvature on surface A here, assuming that my functional map is from functions on surfaces on A to functions on surface B, I should have this relationship, where these are functions that maybe I've written in the Laplace-Beltrami basis. And I could write many more of these things. So for example, the heat kernel signature is also conserved under isometric maps. So maybe I have HKS A at time t is equal to C times HKS on surface B at time t, and so on. I can just write a ton of these constraints. Well, then I can actually recover my mapping C, given enough of these things, by solving a really simple least squares problem, which just says the following. Now careful, our unknown in this problem is a matrix, but given enough descriptors that match from one surface to another, I can actually recover this functional map. Now, another key idea that appeared in the original functional maps paper, and really people have run with since then, is an idea of commutativity. Now, here's the idea. I could take a function, and then I could apply the Laplacian operator to it on a surface. So like I have a function on surface A, I apply the Laplacian to it, and what am I going to get? I'll get another function on surface A. So here's an interesting thing. Let's say that my surfaces are again isometric. Then one thing that we've argued in past lectures is that the Laplace operator is conserved, which means the following. I could take a function and apply the Laplacian operator on surface A. And then I could map it using my matrix C to the other surface. And what I'll get is a function on surface B. Or I could do the following. I could take my function f, the same function on surface A. I could go ahead and map it to surface B, and then apply the Laplacian of surface B. And if my mapping is isometric, then these two things should be roughly the same. So that suggested that we can actually add an interesting regularizer to this functional maps problem, which does the following. It looks at C times the Laplacian matrix of A, again written in the Laplacian basis typically, so it's just diagonal in that case, minus Laplacian B times C, times some, coefficient. And so it turns out that this second term, this commutativity term, is a great regularizer for functional maps. And the really cool thing that's happening here is that this is all written in terms of linear algebra. And it turns out the really beautiful thing about functional maps is just the sheer number of geometric assumptions on our mapping that correspond to linear style assumptions on this matrix C that takes Laplacian eigenfunctions to Laplacian eigenfunctions. So for example, if your map is isometric, then one thing you can prove is that C transpose times C is equal to the identity. It's an orthogonal matrix. So one thing you could do would be to actually optimize in the space of orthonormal matrices to further regularize your functional mapping algorithm. So at the end of the day, what do? You solve just a linear algebra numerical style problem for this matrix C, and then secretly it's encoding a map. And there are also techniques out there. There are actually many of them. I think another one was proposed this year at CVPR that take this matrix, which takes Laplacian coefficients to Laplacian coefficients, and round it back off to get a point-to-point correspondence. Basically, there's a huge space of trade-offs. Well, functional maps are super interesting because it's a nice condensed representation of a map, and it basically converts map computation into linear algebra. It's also a really cool alternative perspective on mapping, and there are so many recent papers with variations and improvements. But it is a little hard to handle non-isometric mapping because you need lots of pairs of features that agree with one another in that case, or operators that commute. But there has been a lot of progress on that in the last couple of years. All right, so functional maps have been extended in like a million different ways. I actually, as an early graduate student, I was lucky to be sort of involved in that research project, although by all accounts, Maxim Yunikov was really the guy pushing it forward. It's been one of the most cited things I've ever helped with. For example, that basic idea of operator commutativity turns out to be a super powerful way to regularize a functional map. And many, many, many different regularizers based on that basic commutativity idea, which really just translates to least squares, which is why it's so popular, have been proposed since that original paper. Everything from building up different differential operators on a surface, using the kernel method, matching curves instead of points, using subdivision, resolvents, so on. Basically, any idea from PDE has been applied in this universe somewhere. There's also efforts to improve the basis for the functional maps. So maybe the Laplace-Beltrami basis is convenient for computing isometric functional maps, but you could imagine other bases for functions yielding map matrices with other nice properties. So for instance, maybe a more localized basis would create a sparse functional map matrix because it takes parts to parts. Or maybe for non-isometric surfaces, you try to compute a basis for functions on the two surfaces that makes them look a little bit more isometric or diagonal. That's what this coupled quasi-harmonic basis idea was trying to do back in, 2012 or so. And also, the linear algebra of functional maps can be extended to handle things like symmetry groups that act on your surface without changing the underlying geometry by looking at, for example, the sort of spaces of functions after you quotient out that symmetry. And there's some really nice mathematical relationship there driven by the universe of representation theory. Now, just recently, there was a really cool algorithm proposed, again, by Max, who really ran with this stuff. I mean, I'd say like 85% of functional maps papers have Max Ovsyannikov as one of the authors, which actually can create pretty dense, high-quality maps between surfaces as basically a small extension of that original functional maps algorithm, which was a little brittle. And the basic technique here is to do sort of upsampling. So what it does is it solves that functional maps linear algebra problem for a very coarse basis, like just a few Laplacian eigenfunctions. And then the sort of trick in this zoom out algorithm is to take that matrix that you've computed using a linear algebra technique and then round it off to one that looks more like a point-to-point map and then kind of alternate. So you solve a linear algebra problem, you round it off to a point-to-point map as opposed to something that's maybe a little fuzzier. Then you upsample and you repeat. And it turns out this is an extremely efficient technique that actually creates dense mappings that are smooth, which is kind of amazing. This is a pretty recent paper, and I'll let you dig into it to read more. And beyond just correspondence, it turns out there's some really nice applications of functional maps for doing things like processing shape collections. So for example, one of the most high-impact works in this space is in this paper with kind of a wordy title, this map-based exploration of intrinsic shape differences and variability. But it defines a particular operator that acts on functions on a surface called a shape difference. And this is a really clever technique. The basic idea was that if I have a functional map from one surface into another, which in this case is this F, and now I have some operator on those two surfaces, like think the Laplacian operator, then I can compare those two by making something like this D. So what do? I can take a function on my surface, map it to the other surface by applying F, then apply the operator on that other surface, like Hn, then map my function back by using F transpose, and then apply the inverse of the analog of that operator on my own surface. So for example, let's say that my map is like the identity map, right? So I just have a boring map from a surface to itself. So in that case, my operator, like the Laplacian, will be the same, and my functional map, my D, will just be an identity matrix. The basic idea is that essentially what you're doing is you're sort of comparing how much the operators on these two surfaces cancel each other out. And so what it does is it allows you to sort of express differences between pieces of geometry by comparing their operators. And so this allows you to do really fun things. Like if I have a shape collection like this galloping horse animation, then that corresponds, after pulling back all these Laplacian operators, to just a big collection of shape differences that starts with the identity matrix and then kind of deviates away from it as the horse gallops and then comes back. And in fact, when I do PCA on the set of Ds I get by mapping frame 1 to all the other frames, I actually recover the animation loop, like what's shown on the right-hand side. And it turns out there's all kinds of beautiful math behind the functional map matrices. I'm very low on time, so I think we'll skip this in today's lecture. But basically, one way that you can kind of understand these shape differences is that they're sort of comparing different inner products on a surface. So for example, if you have a really boring operator, like one that just multiplies by the area element of a surface, you can construct an inner product that's kind of measuring differences between areas. If you instead compute dot products between gradients, you end up with a Laplacian-based shape difference, which compares kind of conformal structures and so on. So I'll refer you to that paper for the details. So basically what you're doing is comparing surfaces by comparing their inner product matrices, which is pretty cool. And this allowed functional maps to be applied to this sort of shape collection style applications, similar to what we'll consider in our next lecture. Incidentally, there's also follow-on work that sort of looked at the set of shape difference matrices and sort of said, given an object and its shape difference to another object, precisely what did I learn about that other object? And it turns out the answer is basically its edge length, like its intrinsic structure. So in the discrete case, you can actually prove this. So this with Etienne Corman and myself, we did this a few years back. That given a shape difference, you can actually recover the edge lengths of a triangle mesh. Edge lengths are not enough to reconstruct a 3D surface, so we also propose some extensions to capture some of the extrinsic structure by looking at not just a mesh, but also its displacement. So in any event, the basic impression you should get here is that the functional maps universe is huge. There's a really nice survey at SIGGRAPH 2017 and some course notes that covers a lot of this stuff. I think since then, Max has also released a book chapter, and I'd encourage you to take a look there. The recent extensions of the functional maps papers all involve this idea of deep functional maps, which couple functional maps with deep learning. And I'll briefly mention this, and then we'll call it for today. Functional maps are kind of amenable to machine learning because they translate mapping from a geometry problem to a linear algebra one. And linear algebra is much more sort of amenable to deep learning style frameworks. So back in 2017, Litani and company proposed the first deep functional maps paper, and this has been, again, extended many different ways, which proposed a deep learning algorithm for computing functional maps between surfaces. So here I'm showing the original architecture for deep functional maps. They called it FMNet. And basically what FMNet did was really simple. It took some fixed shape features on the surface. In this case, rather than using heat kernel signature, they use this other thing called SHOT, which I think is spatial histogram of, I would have guessed normals, but that doesn't start with a T. But in any event, the machine learning happens in taking these shape features and then applying, ResNets or whatever your favorite machine learning architecture to learn more useful features for the mapping problem. And then the functional map is just obtained by putting those features into correspondence with one another and solving a linear algebra problem inside of the deep network architecture. So like it basically is just F inverse times G here. That makes a that makes a functional map C, which is rounded off to a correspondence matrix in this soft core module. And that's what comes out of this functional map network. And in the original paper, they basically just learned these ResNets so that the outgoing mapping agrees with some ground truth maps in data sets. There's, of course, many challenges there, like there aren't that many data sets of not just pairs of surfaces, but like kind of nicely mapped pairs of surfaces. So there's a lot of follow-up work that, for example, tries to learn shape features rather than relying on these shot features, or does self-supervision, where maybe you're willing to assume that you have a shape collection, but assuming that you have a data set of shapes in correspondence would be pretty tough training data to have on hand. And those are just proposed like in the last year. So if you search on Google Scholar, you look at the people that are citing this deep functional maps paper, you'll see it already has been referenced a number of times in the computer vision, like CVPR universe, and has been extended in many interesting and cool ways that incorporate some ideas from machine learning and some ideas from geometry. And I think this really makes a lot of sense. Like, again, as we mentioned at the beginning of lecture today, the mapping problem does have 1 foot in data and 1 foot in geometry. I'd like a smooth mapping, but I also do want to preserve the interesting semantic structure that comes in surfaces. If I map a horse to a zebra, then I want to preserve the legs and the hooves and what have you. And those are the sort of semantic information that these deep learning tools might be able to find. So this is an emerging area of literature, and one that I think we'll continue to see extended more and more in the coming years. In fact, I've been on the committee for a few of these conferences recently and noticed this explosion in the number of papers that propose different variations of deep functional maps and so on. So anyway, that's just a quick pointer, and I'll let you take a closer look at home. So as usual, I've gone over time today, but hopefully you have a good idea of what it means to solve surface correspondence problems in a sort of computational geometry, machine learning, numerical environment. I'll upload an extra lecture segment that goes into much more detail on one of the state-of-the-art mapping algorithms that its job is to compute what we call a reversible harmonic map, which essentially is one of the state-of-the-art techniques right now for computing bijective, smooth correspondences between surfaces. and I think is fairly easy to understand in the language of this course. So I'll record that this weekend and upload it as well as an additional lecture segment. And then it's my goal also to show how these correspondence problems are linked to high-dimensional machine learning through problems in transfer learning. So depending on the time we have at the end of the semester, we might return to this topic and record an additional video on that as well. Basically, some of the language we're using here is exactly the language you need to like map from one data set into another in order to like maybe take a machine learning model that was trained over here and transfer it to a machine learning model that was trained on another data set with similar structure. But in any event, even without that, these correspondence algorithms are a really fascinating branch of geometry. They're applied everywhere from computer graphics to medical imaging, and I think they've really reached an interesting level of maturity that's continuing to evolve from year to year. So with that, hopefully you're intrigued enough to dig into the literature, and I will talk to you next time.